So at Microsoft, like many other companies that work in the data center business, or frankly in industry for that matter, most of what we do in research and development is actually focused on incremental change, optimizing based on what we did the last time. In our case, the last time we deployed a data center, the last time we tried some new equipment, what did we learn? Did it work well? Are there changes we make in terms of either the equipment we use or how we tune things? But some portion of what we do actually is for kind of really kind of if you will, radical things that allow us to explore some totally new space to find out, are we missing big things? Are there different ways of doing things that are much, much different that could give us big gain? And so Project Natick is an example of one of the things that Microsoft is doing in the data center space. So I'm going to first talk about what it is we're doing and why we're doing it, and then I'll talk a bit about the project to date and what we've accomplished. So probably a lot of you have seen the video that's on YouTube, but if you haven't, I'm going to play that for the other folks, just to give you some grounding for the rest of the talk. So you can go ahead. Oh. Now it's not working, huh? Project Natick is a radical approach to how we deploy data centers. Basically what we're doing is we're taking green data centers, deploying in the ocean, off the coast. The overall goal here is deploy data centers at scale anywhere in the world from decision to power on within 90 days. Half the world's population lives within 200 kilometers of the sea.
So moving data centers to the ocean made a great amount of sense to be able to make the actual cable to our customers as short as possible.
The servers are standard type servers you would find at any data center that have been modified for this particular environment since it's in a marine situation.
And then the server has the cooling system attached to the outside. There's all the control electronics that live on the outside of the rack. And then as you move further out, you get to the steel shell. From the steel shell outside, we have all the heat exchangers that are attached to that shell, as well as the outputs for all of our cabling to go back up to the surface. It's kind of like launching a satellite to space. Once you've built it and you hand it to the guys with the rocket, or in this case, our case, a crane, you can't do anything about it if it screws up.
Pump is off?
And pump's on.
Okay, pump's off. Flip switch. Send the divers in.
Humidity's dropping, that's good.
Okay, and is everything stable now?
Everything is stable and on. What's our power consumption?
27 kilowatts.
All right.
And Natick could have a lot of impact, both currently and into the future.
It's not like a moonshot in the sense that it's just some outlandish thing. It's actually a viable product that we could make.
Okay. So we started this project back in August of 2014, and when we went down this path, we were not really worried about whether we could technically do this or not. We knew we could. We didn't know how good it would be, if it would be something to be economically viable. But what we were concerned about is what are the business reasons for why we would do this? And so if you go back to August of 2014, one of the things that was in the news was Edward Snowden. And so as you probably saw in the press, lots of people outside the United States, and by extension their governments, were worried about their data getting snooped by the NSA. And so one of the things that you started to see was countries saying, data center companies, you have to take our citizens' data out of the US and bring it back to our countries. And probably the one that made the most public fuss was probably Russia. And they set a deadline for all the different data center companies to move the data there, and basically nobody could do it. And so they had to back off on that demand. We took that, though, as part of the larger question of how do you respond to the market quickly? And so that was an example of where there's a very fast demand for something to happen. But more generally, sometimes we can't predict what capacity requirements will be for data, storage, or for compute, or for other aspects. And so we set as our first goal, basically, whoops, what is going on here? So we set as our first goal for us, basically, could we do rapid deployment? And to us, that meant from decision to power on anywhere in the world within 90 days. And so when you ask what takes so long, for us today, I think we say about 2 years to build a big data center and get it started. And this is kind of why. So here's a big data center. This is somewhere in the United States. This one runs Azure. And there's an expansion coming. Here's the expansion. The original data center, you can see it all the way up at the top there. So from end to end, this data center is 2 miles. So it's pretty big. Now they come smaller as well, but one of the things that happens is everywhere you build a data center, it's a little bit different. In this case, you can see the topology. It's going to be different wherever we go. The climate is different. The country is different. Even within a country, the workers and the work rules may be different, where we get the power from. And so we're in this situation where every time we build a data center, it's different, even if the design is identical. And if you've ever built or operated a data center, you may realize this. If you've ever remodeled a kitchen, you've experienced what construction is like as well. So the first goal here is to move away from construction toward manufacturing. So much like the servers that we put in data centers, we'd really like the data center to be a manufactured item. And the second question is placement. If we have this now standard data center, can we have a standard plug into which we put it? So for this first piece, manufacturing, industry has already gone here to some degree. This is what's called a containerized data center, as probably many of you know. And it is that sort of notion of it's a standard thing, we fill it with servers, we ship it somewhere, we make it go. But even if we get all of this right and we're happy with this, there's still the problem of placement. And the reality is, everywhere in the world you go, it's hard to get some sort of standardized place. If you're willing to expand your horizons a little bit and actually consider the ocean, things get a lot more standard. First, in terms of the rules that nature applies, it's much more consistent in the ocean, regardless of where you go relative to land in those equivalent places. And secondly, the rules applied by us, by humans, are actually much more standard in the ocean than they typically are on land. So the concept here is to build some sort of a data center that we put in the ocean. And so this particular thing you're looking at here consists of 8 data center pods. Each one of those pods is 12 meters long. And you're looking at about 100 racks of equipment there and about 2 to 3 megawatts of total power capacity. So something like this might be deployed a few miles off the coast and maybe 600 feet deep. And at that depth, the water is consistently cold. So in the ocean, as you go down, it gets colder and colder. And so by way of example, if you look off the coast of Florida, the warmest time of the year, it's never warmer than 59 Fahrenheit or 15 degrees Celsius. So we can get good cooling pretty much anywhere we go. Something like this is what we call a lights out data center, which is to say nobody's there. So the idea is you deploy this, you leave it there for a few years, and we don't see it again until either it's time to replace the servers with a new generation or market conditions change, we want to pick it up and take it somewhere else. The only connection that you'd see back to shore from this is a fiber cable. I'll talk more about power in a little bit. If you look at that purple border there, that purple border is 200 kilometers thick, about 120 miles. Half of everybody lives in the purple. For whatever reason, we are a coastal society. We really like the ocean. So by deploying these offshore near population centers, we can actually bring data centers much closer to people than they are today. Typically, data centers are placed out in the desert or in the middle of nowhere where it's easy to get land, it's cheap, no one's upset about having it there. We don't typically put data centers, say, in the center of Manhattan because real estate's just too costly to do that. So renewable energy is the other piece that we're very concerned about with this project. So everybody's familiar with solar and with wind. Microsoft today, all of our electricity either comes from renewable sources or via carbon credits, and we're looking to get greener as we go forward. Industry started moving wind to offshore, so particularly if you go to Europe, you'll find that there's lots and lots of offshore wind. There's some projects on the East Coast, for example, off Virginia. Dominion, Virginia is a big project coming shortly, and other parts of the world. There's another thing which is called marine renewable energy or marine hydrokinetic energy, which is basically extracting energy from the motion of water. And as you can see here, a turbine, this is going in off the coast of Scotland, I believe. Because water is 800 times denser than air, you can use smaller turbines that spin slower to get basically the same or equivalent amount of energy you get from a much larger wind turbine. So this is the new thing coming. There's different types of energy available, and typically, that slide doesn't look good here, but anyway, you can get energy from the motion of tides, you can get energy from the motion of water, and you can get energy from the motion of what are called gyres. And gyres are these persistent currents or rivers of motion in the ocean. And one that you might be familiar with on the East Coast is the Florida Gulf Stream. So the amount of energy that people think you can extract from the Florida Gulf Stream could be as much as 60 gigawatts. To put that in comparison, the entire US grid, I think, is 40 gigawatts. So, like any other data center, a Natick data center can pull its power from the grid, and actually for our first experiment, that's exactly what we did. When we were starting this project in the fall of 14, a little ways after we'd gotten going, one of the things we did is we looked around, what are the reasons that it might be difficult to get grid power? And you can be sure that Microsoft Cloud knows all these things, but we wanted to pull a few examples. And so at that time, Brazil had a drought going, and as a result of that, it was very difficult to get power. It was very expensive. South Korea, you could get power, but you couldn't get carbon credits to use it. And then other places in the world, it's much more dire. So if you look at sub-Saharan Africa, 70% of the people have no electricity at all. So if you actually want to bring a cloud nearby, you're going to have to bring the power source. So if you look at a data center today, one of the things that you see is this very complicated power choreography. And this is caused by two things. First, power comes in at very high voltage. That's just part of the physics of sending electricity over long distances. But servers want 400 volts or less. So there's a number of different stages where we bring that power back down. We distribute it to different servers. And then the grid is inherently unreliable, as everyone has experienced. And so we have backup generators and these enormous banks of batteries to carry us over when the grid fails until we can get the generators running. We hope to kind of simplify that rather dramatically, at least in some cases, so that you might end up with something like this. And basically what you have is you have a set of independent turbines that are generating power, and then relatively little voltage conversion. And we do this by co-location, so we don't have to convert to high voltage to send the electricity over the grid. And then secondly, a set of independent turbines, so if some of them are down either for maintenance or because they failed, we're still good to go. So we may end up with this much simpler structure, take out a lot of risk, a lot of complexity. So some Microsoft data centers today, people only go there every 6 months or even once a year. So we're gradually moving to this idea of more sort of lights out data centers. And we take that to a much greater extreme with Natick. It truly is, we'd leave it down there for a few years. We'd suffer whatever failures happen during that time and keep going. We have lots of people running around in data centers today that are fixing things because things do fail. But people don't always fix things properly. Sometimes when you're making changes, you can't help but cause some other problem. So we think that there's it's a mix having the people there. But one of the big issues with having people in the data center is just supporting them. So we need lighting, we need space for people to move around, we need a kitchen, we need parking lots, we need security, all those things. So in our model, we take the people out of the data center. Physical access is quite difficult if you're 600 feet under the water. If you doubt that, go read about scuba diving and how deep people can go safely. So it's pretty hard to get there. So in a lot of places, we have unattended data centers, and so these will be more secure. And then there are black swan benefits. It turns out that a lot of weather is really just a surface effect in the ocean. So if you're 600 feet down, even very powerful hurricanes, you may hear them, but you will not feel them. So Hurricane Sandy is not something a data center like this would feel. And then there are some other types of events. So everybody's probably experienced a geomagnetic storm, and typically you might hear about it on the news. There's an aurora very far toward one of the poles, or more likely, GPS was bad someday because satellites were affected. In 1859, there's a thing called a Carrington event. It's named for Richard Carrington, who put together for the first time what was going on in the sun with the effects going on the Earth. And at that time, we did not have very much electrical infrastructure, but what we did have at that time around the world were telegraph systems. And at that time, there was a geomagnetic storm that was very, very powerful. And it was so powerful that if you were in this city, this is 1859, so we don't have a lot of lights out then, but in 1859, you could read a book at night from the brightness of the aurora. It was that bright. It was visible in places like Panama and Cuba. And on the telegraph system, telegraphs failed. Some didn't work, some caught on fire. Others worked when there was no power source applied. Lloyd's of London did a study a little while ago that said if we had a storm like this hit North America today, we're talking somewhere on the order of $1 trillion damage. That's a trillion with a T to the electric grid. If you're deep underwater with only a fiber link to shore, you're immune to this sort of event. So that's interesting from the standpoint of diversity. Today we do georeplication of people's data across data centers, so this is another form of potential security for things like business continuity. So if you put it all together, you might get something that looks like this if we build a data center at scale. So you're looking at about 20 to 30 megawatts of data center. There'd be some set of turbines in the area generating power for the data center. And we get a few things out of this. So remember the speed and agility to respond to the market quickly, going to manufacturing instead of construction. So we move toward every data center really is identical in its behavior rather than every single data center is unique. We get close to customers by locating near population centers offshore, and of course, co-location with renewable energy. Okay, so that's kind of what we're doing and why. And so to give you an idea of what we've done so far, I'll talk a little bit about phase one. So when we were getting started, we're computer people. We don't really know about the ocean. It seems like a bad idea mixing water with computers, so we're kind of a little not sure how this is going to work. So we had a very simple set of goals. Let's just put something in the water for a month and see what happens. And there are a few particular things that we were really concerned about, one of which was, can we keep it dry? Can we keep it cool? Can we really operate truly hands-off? Because there is no way we can go and kind of reboot something by hand or change a connector. It's just not happening. And we wanted to understand what was the interaction with the environment that we were in. So if you go back to 14, at that time, at least as we were looking around, people were talking about, well, let's put computers in mineral oil. Or let's use kind of some of the very fancy chemicals like Cray computing used to use for supercomputers back in the 70s and the 80s. And so we went and we explored a bunch of these different cooling options to really understand them. And so we looked at different types of fluids, different types of liquids we can immerse things in. We looked at boiling liquids. We looked at different types of gases. We looked at supercritical fluids. And what we found from looking at that is three different things. First, there's actual real merit to some of these different approaches. You really do get value in terms of cooling, but at the expense of changing the supply chain, because a lot of electronic equipment doesn't work just off the shelf in these environments. And also, a number of these different compounds that people are talking about using have environmental problems. And in fact, some of them are on the greenhouse gases no-go list, or soon will be. The second thing that we learned is, in a lot of cases, if there's the very fancy chemical, you can find chemicals that are 1/10 or 1/20th or even 1/80th the cost in one case that work just as well. But the key thing for us that we found is for anything that we plan to field either soon or even in the midterm, there's no benefit to us. We can use something much more simple and do just fine. And so that's what we did for the first time out. So what you're looking at there is a cutaway of the thing that you saw in the video. And so what we have literally is we took a 42U Rittal rack and we put some Microsoft servers in it. We tipped it on its side just because of the particular test we were doing. And on the back, we put an air to liquid heat exchanger. So hot air comes out of the servers, it's cooled. That heat exchanger then communicates with a heat exchanger that's outside, which is then cooled by the ocean. I'll give you a picture of that a little bit later. So you can kind of think of this as your car's cooling system only in reverse. So in this case, we're using cold ocean water to cool hot air. This, unlike the containerized data center example I gave you earlier, is truly sealed because it has to be. And that allows us to do some other things. First, it's dust-free, so we don't really care what the environment is outside. We're not going to worry about dust getting in and causing problems. But also, we've changed the atmosphere. So we're using 1 atmosphere pressure, just like we have in the room here, but it's a nitrogen atmosphere, it's dry. So we've taken out the oxygen, we've taken out water, which we use a lot of in data centers today. So issues with corrosion on connectors that cause us to have to go in and receipt boards, we expect to largely go away in this kind of an approach. And also, this is a manufactured item. So the idea is we'll build these in a factory, we'll fill them up with servers, so the same organization does the whole thing. So we've got consistency, it's ready to go, we can give the servers truly the same experience anywhere we go in the world. And I will tell you that within Microsoft, if we take the same exact hardware and we deploy it in different data centers, we can tell. Each data center has its own failure signature, even though the servers may be the same. So we expect to get away from that with this. So a little unnatural for Microsoft, but we built a pressure vessel as part of this project. And so you can kind of see there on the right, that's in the factory before it's been painted. So it's 3/4 inch thick steel. It's good down to that 600 feet depth, although we used a lot less this time around. And that's our data center. Here's our rack in the shop. And so it's just a 42U rack. The big black thing on the back is the heat exchanger. It's on a door that we can close. And all that stuff you see on the left side there is basically the plumbing. It's basically a pump and some measuring equipment that allows us to sort of basically flow our coolant, which is tap water, between the internal and the external heat exchangers. So it's a little bit of a Frankenstein thing, but really this first time around what we were looking for is just the ability to measure thermal transfer. And so we had 3 Microsoft chassis in there, which are these 12U units. So one of them had 12 servers, and the other 2 were filled with what we call load trays. And the load trays are basically just giant resistors that we use to measure the cooling in data centers when we're commissioning them, because we just wanted to generate as much heat as we could. So this is it going in the water. Those copper-looking grids that you see are external heat exchangers called Cubefloors, which are a commercial product. They're sold for small boats for cooling the engine block. Sits on the bottom of the ship. We use these because we knew it would work. What we were really interested in, though, is if you can kind of see toward the top and on the right side, this sort of silvery spaghetti thing. That's a heat exchanger that we designed. And the purpose of that heat exchanger was to get us much better heat transfer than we get from the keel coolers, and also the ability to go to very deep water. The keel coolers will not go very deep. And so that heat exchanger that we have is as good as those 4 keel coolers combined. So having never done this before and not knowing what would go wrong, we put lots and lots of sensors in it. So we could understand not just what was going on with the servers, but the internal environment, temperature, pressure, humidity, things like that. We wanted to understand outside in the water, what's the water temperature, what's the water pressure, because really our cooling capability is relative to whatever the external temperature is, as well as current. We also had the ability to measure fluid pressures and temperatures and flow rates through the cooling system. So we did all that, and so we pulled this out of the water last fall, and what did we learn from all of that? Well, I think the first thing is we had planned to go in for a month, and after a month everything was fine. So we decided, well, let's just keep going, and we'll see what breaks first, what happens to us. And ultimately we were in the water for about 3.5 months, and eventually pulled it out because everything was still fine. So it's not statistically significant. It's a very small number of servers, but obviously if we had been flooded or if things had started to fail in some strange way, that would have been indicative. So we were quite happy with that. The heat transfer was great in that when we were done, our heat exchanger had the same heat transfer capability, as just as efficient as when we started. And that matters because one of the things that you get in the ocean is so-called biofouling. So you might have noticed in the video, you saw the shell, there's random stuff kind of accumulating on it. We didn't get any of that on the heat exchanger that we built. There's various different techniques for doing that. We tried some of these when we were in the water. This notion of biofouling things growing on you basically starts single-celled organisms establish themselves and the things that eat them and so on and so forth until you get to big things that are macroscopic in scale, like barnacles, and then you're in trouble. And so there are 5 different things that kind of promote growth. So light, warmth, oxygen, nutrition, and lack of current, so stagnant water. And so we deployed this in California where the water was between 14 and 18 Celsius, which is pretty warm for the ocean, and just 11 meters down, sunlight easily penetrated, lots of nutrition, lots of oxygen. So that gives us a lot of confidence to go to sort of environments where it's deeper and it's darker and there's less problems with growth, which is where we typically deploy. So as I think about the value out of this, there's really kind of 2 categories, one of which is sustainability and the other is more direct business benefits. And so in sustainability, the first thing is basically the green energy. So getting away from the carbon emission. And because of the type of cooling system that we use here, there's no exchange with the seawater. We're not consuming water, which as some of you may know, if you go to places like California that have drought situations and many data centers, people are not happy. A typical data center, large data center, can use as much water as a small town. So this is like a big deal to be able to get away from that. The cooling architecture turns out to be very efficient. We just have this small, simple little loop that we're doing. And the power architecture, to the degree that we can kind of actually sort of elide the grid, is valuable. The Energy Information Administration says that every year in the United States, about 5% of electricity generated is lost as it goes across the grid. And so if you have a big electric bill like Microsoft, that's real money. Another thing that may not be obvious, but if you actually tally up the material per server from the data center, we use much less for this than we do for data centers, we believe. And so that means in terms of impact on the overall economy and the environment from generating and transporting all these materials could be a lot less with something like this. So business, so agility, be able to get to market quickly by having a just-in-time supply chain, all the benefits that come from that in terms of driving down cost and getting consistency in terms of the data center and the experience of the servers we deploy around the globe, getting close to our customers, better physical security for unattended data centers than what we have today. And haven't talked about it, but you've probably all seen in the press about Moore's Law. So this is the notion, right, that every generation servers get cheaper, they get faster, they use less power. And it's kind of really winding down. For the last 15 years, there's not been all that much benefit in terms of cost, in terms of performance. So what that means to us is historically, we want to replace servers frequently in our data centers, maybe every 2 years, because if we don't, our competitors will do that. They'll have some advantage over us because they've got the newest, greatest stuff. The pace at which that's going to happen is going to decline. And what that means is we're going to care more about the reliability. Today, we don't really care if we can make a server last 10 years because we're going to swap it after 2. But if we're going to keep servers for 4 or 5 years, somehow, at that point, all of a sudden, error rate becomes a very important thing to us, how quickly these things fail. So we think providing this very consistent environment that's consistently cold, it's dry, it's stable, will help us reduce error rate, keep servers longer, more effectively. So I'm going to end by talking a little bit about cooling, because I think everybody knows about cooling in data centers. It's not, to me, the most important thing that we get out of this, but it is tangible, I think, to a lot of folks. So we started, if you will, with mechanical cooling and things like chillers and DX, and that's great. It gets us these cold temperatures, but boy, it uses a lot of electricity, maybe as much as 80% on top of whatever the servers are doing, and it uses a lot of water. And then more recently, a lot of us have moved to this notion of free air cooling, which is nice because it really drives down the cost of the power. But it does that at the expense of letting the temperature in the data center rise a lot higher, depending on what the outside temperature is. And there is some impact on reliability from doing that. But overall, it's been a good trade. It uses less water. We've been happy with it. So for Natick, this is kind of what we think we get based on our experience so far. We'll get the cold temperatures that we got from mechanical cooling, but we'll do this with really, really low energy expenditure to do the cooling. Sitting in a vat of cold water is enormously efficient from a cooling standpoint. And we'll do this with no consumption of water whatsoever. It's just a sealed system. We're just using the ocean to kind of dissipate heat. The other thing here is, as we think forward, we're looking at 1,000 watts per U as our cooling capacity, which is much higher than most people do today. And we do this with a very small space. So we don't have big space inside the pressure vessel for hot and cold aisles. So we think this is a good thing. And again, with some of the characteristics I talked about for a nice, clean, sealed environment. And to do this in a way that we're not using exotic materials or coolants as some of these liquid cool systems that people talk about are using today. So that's what I've got. I'm happy to take any questions.
Questions, folks? So what are the next steps in terms of looking at how you move forward and develop this concept?
So right now we're planning what the next phase of this would be. And we haven't really talked details too much, but I will tell you that physically it might be 4 times larger. So that means about 12 meters long. So think about a shipping container you might see on a ship, that form factor in size at least, and perhaps 20 times the server, so maybe 0.5 megawatt.
Quick question about longer term. I mean, you mentioned even in the first release, there was mention of the potential benefit of actually increased growth of sea life, as it were, around the data centers. So I guess 2 questions about that. One, I have to imagine that replacement is a pain in the ass to some degree, albeit you may have longer life for the average server, which is positive. But what happens when you have to tear apart all the sea life to put the servers back in? So
it turns out that there's a whole field almost of artificial reefs. And it's a complicated thing. So you sometimes hear like we're dumping a bunch of rail cars off in the ocean and great stuff will happen. It turns out that you have to be very careful with what you're doing because sometimes what happens is you put a new artificial reef in and you get selective migration from some other nearby natural reef and that other reef dies. So there's a whole art of how you construct these things and what sort of structures you put on them so that you can kind of promote life without sort of otherwise damaging the ecosystem around you. And that is an active area of research. We've got some academics that we're working with on that. And so part of what your question was is, okay, now that I pull it out, what do I do? And so one possibility is there will be some leave behind a structure that will sort of continue that. So you can almost a shell that comes off and the rest of the thing pops out. It is a complicated field. I think that there's a lot of debate about whether artificial reefs are a good or a bad thing, but it is an area that we're looking into because, again, we don't want to kind of damage the ecosystem wherever we go.
And don't need to take away. I think the project is fantastic. So great work.
Yeah, thank you.
Question about the technology refresh. At every 2 years, it's certainly going to take less time to do a technology refresh in a standard data center than it is in your Natick. How is that going to impact the long-term viability of the system?
And so why do you think it will take longer in this?
I think you have to recover it.
So think about you have to recover it. But I've got a data center, a standard data center. People have to go through. They got to pull all those things out. So in my model, you build this data center, right? It's a shell. There's a factory. We just slide a bunch of servers in, right? They're pre-assembled and off you go. And then similarly, when I take it out of the water, it's basically the same thing. And just sort of slide in the new set and back out in the water. So I can kind of do that in a couple days. A day to take it out, probably a day to refurbish it, then a day to send it back out. So it should be quick. So there's different ways of doing this. So the first time we did it, it was actually sitting on the ocean floor. The concept video you saw, or the concept image you saw, it was actually moored in the stream. When we started this, the theory was that we needed to be moored in the stream in order to kind of get good current, get good cooling. And I think what we learned is we really don't need that. And it's much simpler to put things on the bottom. And so that's possibly where we'll go, but I think that's an area of active discussion. For energy, you do need to be somewhere higher up. But we ourselves, we don't think we need that.
Once you achieve economy of scale, do you have a sense of the comparable cost of the traditional data center to build and operate to this project?
We do. I think we're not going to talk about that today. But I will say generally, you can kind of look at the different costs that go into a data center. There's the building, there's the operation, there's the servers, there's the network, there's the electricity. And so the pieces that we sort of directly affect here are basically the data center itself, the operations of the data center, the cost of the electricity, and then the servers is kind of a complicated mix, right? We think they'll last longer, but also in a data center, I can just swap out a server if it fails. Here it's just dead until I retrieve this thing, so I have to include that added cost of having had that server that's not useful now. And so even with all that, we think that this is better than data centers. But again, we don't know yet. We did this very small scale thing. After we do this next phase of the project, we'll be at some scale where I think we'll be able to sort of know definitively, economically, is that true or not.
I would assume you have lower costs, being that you're renting or buying water rights, for lack of a better term, and how do you go about doing that with local or federal governments?
So it turns out that's a complicated thing. But much like on land, where I have to not just sort of buy the property, but I have to get the rights to put stuff there and so forth, you've got the same thing in the ocean. It tends to be more standardized how it works, and it depends on where you go. So for example, in the United States, I could be in state waters or I could be in federal waters. Different authorities are involved in this. But there is some whole process. So the idea is, in some sense, you pre-permit wherever you want to go, and then once you've got that, I can kind of easily add or remove things over time. But there is a whole process there, and it's something that we've had discussions with different parties regarding that. Even to do a test, right, you have to get kind of the appropriate approvals. So, anyone else?
Without current, is this a viable proposition for, say, Great Lakes? You've got highly populated areas around the Great Lakes. Have you explored that possibility?
So I think kind of large bodies of water are fine. The things where it would not be fine is if I had, say, a small body of water that has no current flowing through it, because you will kind of, probably have some impact on the overall temperature there. In our case, where we're looking at the ocean typically, basically you can kind of look at the water, this, if you will, if there's just a mild current, and the ocean, there's always some current. Just downstream of a vessel, you're probably a few thousandths of a degree Celsius warmer than you would be upstream of it. If we look at Bureau of Ocean Energy Management, actually has some guidelines for the amount of energy density they'll allow for extracting energy from the water. If we imagine we take all of that energy and immediately turn it into heat there, at whatever the limit is they allow, outside or just downstream of one of those lease blocks, the water on average would be about a few millionths of a degree Celsius warmer. So as long as there's some current around, it's fine. I think the Great Lakes are big enough that it would be fine. Even though these numbers sound big, if you actually look at kind of like a cruise ship or something like that, you're talking in the mid-tens of millions of, maybe as much as 50 megawatts of power for the engines, all cooled by the ocean. So overall, we're kind of pretty small. The big issue is not so much the energy that you put into the ocean or the atmosphere. The big issue is greenhouse gases, right? So it's the retention of this stuff. So getting away from greenhouse gases is really, from an environmental standpoint, the important thing.
I have two questions. One is, I understand that at depth, the surface conditions wouldn't affect your data center pod, but doesn't it affect your power sources? And the other is, why the name Natick?
So on the first question, absolutely it's going to affect the power sources, but the folks who are in the business of generating energy are going to have to figure out how to do that, and they are much the same as if you've got wind energy in the Great Plains here, and you've got to worry about all sorts of weather that will come by. So same issue there, but again, people understand the ocean. We've got a very vibrant industry out there that's represented by shipping, oil and gas, subsea cable, marine renewables, all that stuff. Natick, we actually got asked that question by the local Natick newspaper. And we also heard from the Wellesley newspaper that wanted to know if they would be next, because they're the next town over. The truth is, this is true. Anyway, they're just random names. We just sort of, for projects inside Microsoft Research, just generally pick random names of cities, big and small, just as code names. So there's no real meaning to it. Good? All right, thank you.